Welcome to JCON! Welcome everybody, good morning. This talk is all about rethinking microservices persistence, and I'm super happy, Mark, that you join my session here, or we do the session together, thanks. And Richard, you only forgot two things. So here is two announcements. And one announcement, here is a new JAVAPRO magazine, printed magazine. But I guess it's already sold out, right? Isn't it? Okay. Actually, we should get more copies to the conference. But you also can get a PDF version of this, and you'll find a lot of more articles online. And thank you to all of the authors who wrote articles. It was really very close to produce this magazine, and yeah, thanks to all speakers who submitted a proposal. So we will continue, and we will try to launch a special edition at least twice a year for new Java releases, maybe another release, another copy for JCON especially, maybe also for other conferences. And then I want to, because we have forgot one guy, and I'd like to thank you to Thomas Schmetzer, who is our CFO at Microstream, and he's also a co-founder of JAVAPRO and a co-organizer of JCON from the beginning. But he's kind of the hidden face. Thomas, are you here? No. Okay. He was not able to come, but so he was. He's the hidden face of organization and cares for all the complicated stuff, legal stuff, and also for finance. And at the very beginning was very difficult because of running conferences is expensive, and so we had to save money. And Thomas was able to make it, and there were some cool stories when he really measured the cakes we ordered. So he measured the size of the cake, and then we found out they were too small, and so we got a 50% off and something like that. And so we were able to save money. And this is Thomas' work. Thank you, Thomas. My name is Markus Kett, CEO, co-founder of Microstream, and co-organizer of the JCON conference. And I like to announce again what we have done the last years and months for the Eclipse Foundation, or within the Eclipse Foundation, what we have built and what we are working on. So this is most stuff maybe is brand new to you, and now we talked about on Monday and on Tuesday about this new stack we're going to launch at Eclipse Foundation, and today I have additional news. But first of all, let's talk about the Eclipse Foundation. And it's because of when people stop at our booth, and mostly they say, okay, I have some questions about the Eclipse IDE and some tips for improvements. But Eclipse is not only the IDE. So within the Eclipse Foundation, we run more than 100 projects, more than 100 open source projects, and also the specifications are created, specifications and standards for the frameworks you use every single day, like Jakarta EE. and microprofile, and there are a lot of famous open source projects actually. So Chatty, for instance, Eclipse Link. So go to the website, check it out. There are a lot of cool open source projects. And we announced on Tuesday, the Eclipse Data Grid, and it's just a working name, so it's not confirmed already. And it's a kind of in-memory data processing layer, or you can use it as a caching layer, as a caching platform. And it's the complete stack we have built for the last 10 years. So here are the core components of this this project. So the Eclipse Data Grid is, most of this is core Java. This is the cool story behind this. It's because Java is very performant and provides you everything to process data in memory extremely fast. Then we add a persistence framework to Java. Actually, this was the concept. We wanted to add persistence to the programming language, actually. So we worked on Eclipse Store. And Eclipse Store uses the Eclipse serializer for storing objects on disk. And we run OpenJ9 because it fits great. Of course, you can use other JVMs, but we will talk about why OpenJ9 is great for this use case. And on top of that, we now release the whole cluster infrastructure that you can run distributed Eclipse Store applications under EPL license, and you can use it for free of charge. You can use it for commercial applications and proprietary applications. Who of you uses or knows Eclipse Store already? Okay, quick introduction, and then I talk a little bit about what we're working on right now. So beyond Eclipse Data Grid. So the concept is storing data, storing objects, and it's obvious. Or the last 50 years or so, we use databases, of course, but we believe more powerful to process data is to use the programming language, and Java is great for that because it's extremely fast. And everything that's executed in memory is executed extremely fast. We talk about microsecond search times, response time, because it's executed in memory, of course. So why not using this performance? And we have a great data structure. So database vendors, they're working on multi-model structure to cover everything. But in Java, we can cover everything because we have Java objects. We have object graphs, interconnected objects. You can design it freely. You can use all types, all Java types, collections, documents. We can deal with graphs. Of course, there's an object graph. And we can deal with vectors. So everything is possible in Java. That's awesome. And there is a query language, Java Streams API. You can search, filter on object graphs in microseconds. So even if you have really complex data structure and you have huge object graphs and ton of data in memory, you can search and filter in microseconds. And when we talk about database performance, we talk about milliseconds. Milliseconds and microseconds, this is a difference. This is extremely huge. So we talk about up to 1000x faster searching and filtering in memory with pure Java. The only thing missing so far was persistence. Was not possible with pure Java to store objects. So this is why Hibernate was invented. So to store objects in a database. But actually you don't store objects, right? It's converted to something else. It's SQL is generated. But we wanted to do the Java native way, to use that you can use the native Java object model as it is. Design whatever you like, it can be stored. This was the idea behind. And now with Eclipse Store, you can design any object graph, any complexity, circular references. You can use all Java libraries, everything, all Java concepts, and you will be able to store it persistently on disk and restore it in memory when needed. And you can also store subgraphs and restore it, so loading subgraphs in memory very easily. Fully object-oriented. There are no classic selects anymore, so you just access the object graph with get methods, that's it. And to store objects, you call a store method, and then it gets persisted. By using the Eclipse serializer, the Eclipse serializer enables you to store any complexity, any complex object graph. And yeah, you can use any types, that's possible. Eclipse serializer is creates a binary format and a binary representation of your objects in memory and stores it to disk, or stores it wherever binaries can be stored. And this concept is not new. Online gaming companies or banking companies use this functional principle for a long time already, but they had to build their own in-memory database system. This is effortful, time-consuming, it's super expensive. You don't want to do that, and this is now, Eclipse Store is now a framework for you, and you can use this concept. And all further challenges, like what's if my classes change, lazy loading, do I have to load the whole object graph in memory? All of these challenges are solved. And now also the distributed environment is solved. A lot of people told us, cool concept, sounds interesting, but for searching and filtering with Java streams, I have to load a ton of data in the memory if I have really huge collections. Now we introduce a component, a library called GigaMap, which introduces indexing and fully automated lazy loading. So it's a kind of like, yeah, imagine there is a big table and you can operate on the table and everything is loaded into memory automatically, and the memory management is covered by the JVM anyway. So extremely easy to use, and this is also now part of the Eclipse data grid. So far, the concept was built for single JVM applications. That's cool, because monoliths are great, right? But people told us, yeah, they are great, but we don't use a monolith anymore, so we need a microservice architecture, or we need distributed applications in any case. So we cannot use Eclipse Store. So we worked on a distributed system that enables you to distribute your object graph through hundreds, thousands JVMs by using replication. We launched this solution some months ago, and now we open source it. And you get this whole functionality with the Eclipse data grid. You can run this on-prem. We also provide a SaaS solution for that to evaluate it and to test it very easily. And the cool thing is, so the architecture now looks like a distributed cache or maybe other solutions you already know, but the main difference is you can use the native Java object model as it is. No data conversions, no conversion to JSON or something like that. The pure Java object model. Searching and filtering in microsecond response time, caching, you can use it as a cache layer between your application and your database. And this brings me to microservices. So this solution is released under EPL. The last days we talked about, or people stopped at our booth and asking, when can you release it? So there is a cycle in the Eclipse Foundation, takes some time. So we ask, when do you need it? We want to start it next week. Okay. Oh, this is very close. But we will be able to make it. So we try to release it next week under EPL license, under the roof of a MicroStream, and then starting the Eclipse internal process, and hopefully we can launch it some weeks later as the Eclipse data grid. Microservices. So this brings me to distributed application and microservices. So now with this Eclipse Data Grid, it's now ready for microservices. That's great. So, but you also can use it for migration, for your migration path, for migrating a monolithic application to a microservice infrastructure. And it's because maybe you have to do it anyway, and because we never would build an application or a microservice application for 3 years, migrate the application for 3 years, and then switch over from the legacy application to our new microservice infrastructure. So we have to do it anyway, step by step. So module for module, service for service. And this is a great use case where you can use the Eclipse Data Grid. Microservices, I think the functional principle is pretty clear. So with microservices, we split the monolithic application into numbers of services, mostly using domain-driven design. The services run in their own container, isolated on our container platform. I guess this is pretty clear. And the advantages, benefits of microservices are also pretty clear, because you hear this all the time, constantly on conferences, read in magazines, and so on. So let's repeat it. So easier development, of course, faster deployment, great flexibility, improved scalability, granular scaling, right? Optimized resource utilization and cost optimization. That's great. You get this with microservices. Who of you uses microservices already? You're very convinced. Great, cool. Now the people tell me, after we have built this cluster solution, we go back to Monolith. Now the interesting thing, and what we are working on right now, what's coming next. So when we have a look on common infrastructure, then we can see something like that. So microservices, distributed, serverless, everything's great, and there is a database. So we were wondering, why actually are databases still monoliths? And when we discuss this with database pros, then they tell us databases are not monolith. They are distributed. They can introduce sharding, so they are not. They are not monolith. What do you think? Are databases monoliths? Who of you thinks databases are monolith? Okay. So what happens if I distribute a business application? I run a monolith as a distributed application. Will this be a microservice architecture? Who thinks this is a microservice architecture when you just scale your monolithic application horizontally? Who thinks this is a microservice infrastructure? Yes, thank you. Nobody agrees. So, but a distributed database is still, in my perspective, a monolith, because the database management system itself stays a monolith. So you can distribute it, of course, then you can distribute the load. It supports sharding, that's great. But when you scale the database nodes, then you can see you scale a huge server database. So it's not so granular. And now we were thinking about building a database system that is based on a microservice architecture. And then this would look like this. So there is not a database server you scale horizontally. There would be hundreds or thousands or 10,000s of micro databases. And we connect these micro databases with the object graph. So when you access your object graph by using Eclipse Store, and you load data by just calling a get method, then with this concept, there would be a micro database started in the behind the scenes, and it just consumes maybe minimize of resources. So it's 1,000 times smaller than a database server, just for loading this lazy reference. So we invoke a micro database. It delivers the data, it caches the data, and it's only running as long as you need the data. If the data is not required anymore, the micro databases are shut down. This is a Lambda functional principle, serverless functional principle, but on the architecture level. And this is what we are working on. With this functional principle, you can build highly scalable and very flexible scalable databases, database applications. And then we are working on a similarity search for Java and pure Java approach. And in combination, this will become a micro vector database network, and you can use it for storing any data, processing any data, but of course for Gen AI projects with Java, for Java enterprise applications. And the goal is it saves a lot of computing power, energy, and cost. And this is very important for AI at scale. And so this is what we're going to achieve right now. And why this all is so performant and so fast by using Java, pure Java. This is what Mark is now talking about. And if you like the project, please start on GitHub. This is very important for us. If you have questions, please stop at Eclipse booth, and we can answer the questions. Here are the people who write the code. Thank you. Mark, please, it's your stage.
Hi, everybody. So if you don't know me, my name's Mark Stoodley. I'm from IBM. I'm called the chief architect for Java at IBM. My background is actually computer architecture and compiler optimizations, but I have written a few lines of Java in my time as at IBM. 23 years I've been working there, building, testing, and deploying Java runtimes for IBM products and customers. And I've had the honor of being able to get involved with all of the activities that IBM's been having around open sourcing a lot of its technology. That happened about 10 years ago now, almost 10 years, 9 years. And I got the pleasure of leading a bunch of that, and for that they made me a chief architect. I have a question for everyone. I wanted to start off with saying, I want everyone to answer this question by raising their hand. So who here is sitting in a movie theater? Amazing, we're all here. Okay, good. No, keep your hands up. Keep your hands up, keep your hands up. Come on, hands up. All right, now, put your hand down if before Richard stood up, you weren't really familiar with OpenJ9 or IBM Semru runtimes. Okay, that's good. So there's like maybe a quarter of the audience knew it. Okay, good. So that's the reason I'm here. It's because 3/4 of you don't know about this great stuff. So I'm going to talk to you about IBM Semru runtimes, which is IBM's JDK distribution, which is the only open JDK-based distribution that is including the Eclipse OpenJ9 Java virtual machine. It's a drop-in replacement for any JDK, 100% open source, public downloads updated quarterly, just like every other JDK distribution. Lots of platforms that we support. And it's very well known for providing faster startup for Java applications and using low memory footprint. So it's a really good fit for microservices and trying to drive high performance for microservices in resource-constrained environments. As you can see, it's basically just a combination of the class libraries from OpenJDK plus the Eclipse OpenJ9 Java virtual machine. And just in case you're not familiar with the name, Semru, Mount Semru is the name of the tallest mountain on the island of Java in Indonesia. So we thought that was a nice connection to Java. I like to say it's the part of Java that's in the clouds, because fast startup and small footprint are really good features when you're trying to run in the cloud and you have to pay for all your resources. And I have also the honor of having come up with that name. Unfortunately, it's also an active volcano, so sometimes we have to be a little careful. All right, so what were we trying to achieve when we build our own JDK? Why do we have to build our own JDK? We have to support hundreds of different Java products, ranging from monoliths all the way down to microservices. Basically, if you can imagine a question about the characteristics of a Java application or the environment it runs on or the systems that it needs to support, there's somebody important who's going to say, yes, I need that, or I have that, or I do that. And so we need a JDK that can really flexibly adapt to the environment that it's in and meet a wide variety of different performance metrics. So the key ones that we're watching up there are startup time, memory footprint, response times, throughput, CPU usage, etc. And so as we, as a team, are evolving our JVM technology forward to try to improve on all these things, because if you ask people if they want more of X, the answer is always yes. But that's really hard to do. You have to meet different goals for different user groups. I can't necessarily just go hammer on startup time and only improve startup time if that's going to make throughput a lot slower. I have to balance all of these things. And no single thing that I do in the JVM is likely to be able to support the needs of everybody. So I have to get into this multi-tool kind of approach. So we employ multiple tactics to optimize all the way from tiny microservices all the way up to massive monoliths. And when I say massive, I mean massive. So as you can imagine, IBM's customers range from individual developers all the way up to Fortune 500 companies with hundreds of thousands of deployments. And sometimes those things are really big. And they need to be running efficiently too, because they run the economy. So we kind of want that to work well. So there's this kind of semi-myth that I want to try to correct about OpenJ9. I've seen people write it in different blog articles that OpenJ9 favors memory and startup over performance. And that's not quite the way that I would say it. I would say that OpenJ9 aims for a more balanced approach where we don't unduly favor raw speed. So yes, raw speed is important, and there are customers who will tell us that only raw speed matters, so yes, we do have to pay attention to it. But we also have to be able to do other things. And so I like the way that my performance architect said it to me recently, which is that last 10% of raw speed might be better spent on something else, on improving startup or footprint or CPU resource usage. You might kill yourself to get another 10% in performance because everyone's been pushing on performance for so long. But if you don't go for that last 10% in performance, maybe you better spend those resources for other things. So I wanted to talk a little bit about how we've been evolving the performance of OpenJ9 since we open sourced 9 years ago. So I thought I'd put up this nice simplified graph. Hopefully everybody can see it everywhere. So I've kind of split the life cycle of a microservice. It doesn't have to be a microservice. Monoliths behave this way too, but it's basically a transactional workload, right? At the beginning of the run, you're starting things up. You started Java, the JVM has to get going. Your application framework like Quarkus or Liberty or Spring Boot has to get up and running, initialize its data structures, load the application. All that time, you're doing nothing. Like if transactions are showing up at that time, dead in the water. You're not processing anything. Eventually, you get to this first dashed line here that I've got, and you respond to your first response. Yay, some customer's happy. Fantastic. You gave the answer that you were asked for, but there's all these other ones still there. And the code paths in the JVM still have to warm up. You have to do a bunch of JIT compilations. You have to load a whole bunch of classes. You have to initialize caches and fill in caches and figure out what you're doing. And so over time, the performance of your application goes up, ramp up. And then eventually all that stuff gets filled in and all the code gets generated that you needed and all the classes get loaded that you needed and you're hit this steady state. And then from that point forward, performance doesn't change dramatically, hopefully, unless you got a memory leak, which I don't recommend. So obviously this is a very abstract, nice, simplified. The real curve looks a little bit more noisy. Probably nothing like that. It probably looks more like, it's like this. But you get the basic idea, right? So when we start, let's pick an arbitrary point in time in the history of OpenJ9, we had some graph that looked like this. And yeah, I know I haven't put anything on the axes to tell you where we were or what we look like, but we were competitive, are competitive with other technologies out there, because if we weren't, IBM wouldn't spend all the money to build this stuff and pay a team to do all these things if they could just get it from somewhere else. So it has to be good, because otherwise we wouldn't be working here on this. And so let's see. So if I'm just going to give an arbitrary performance report card. My daughter's about to get to the end of her term now, and so she's in the mode of thinking about grades, so it got me thinking about performance scorecards, report cards. So I'll say, this, go back, there we go. This startup period isn't great, right? We know that there are other technologies out there that can start faster than we can. There are some that start slower than we can. So I'm going to give it just a B. Ramp up time, this seems to take like a long time, and nobody really likes this. So I'm going to give us a C there. And then throughput wise, as I said, we're trying to balance things, so we didn't expect to be at the top of the heap. But we're pretty good, very competitive, and so I'll give us a B. And so where can we go? Where did we go from there? So a few years back, we started investing in a technology that we call Instant On, which leverages Linux's CRIU, checkpoint restore in user space, to basically take a JVM process and store it to disk, and then you can distribute that image to all your different deployments and just resuscitate it, and it comes back really quickly, and you can start a full Liberty Jakarta EE massive application in a few hundred milliseconds, right? That wasn't possible before we could do this kind of stuff, right? No restrictions on what Java programs you write or what Java features you use. You can do this. You don't have to change your application, and you can get that kind of startup with WebSphere Liberty and OpenJ9 running under the covers. And so the effect that had was it basically shifted this whole curve backwards, right? So I'll start here. Instant On allows us to start up a lot faster, just a few hundred milliseconds. And so startup time, okay, we're up to A, I think, at that point, because once you're at a few hundred milliseconds, the difference to any of our competitors is marginal, I would say, because you still need to start up a container, and that takes hundreds of milliseconds. If you're working with Kubernetes, you have to start up pods and nodes, and those things take even longer to start up. So if you're down at the level of a few hundred milliseconds, my argument is that you're probably in the right place already for most use cases. Not all, but most. Seems to satisfy a lot of our user base. And then the second nice effect of that is that because we started earlier, even if you don't even change the ramp-up curve, the ramp-up happens faster, in a sense. You get to this point earlier than you did before. So, we'll change our C to a B. We got a little bit better. So, but can we improve ramp-up even more? So we invested in a technology called the Cloud Compiler, the Sumeru Cloud Compiler. At Eclipse OpenJ9, we call this JIT server. The basic idea is you take the JVM, you take the JIT compiler out of the JVM, and you make it into an independent service. And you can deploy that remotely. You can give it as much resources as you want. You can scale it up, you can scale it down, and you can basically apply JIT resources independently of what the JVM is using. And that allows a much nicer resource curve in your Java application. It performs very well, very nicely. You don't end up using much more memory than you would at steady state. It's a very clean curve, and it's a very low memory because it's OpenJ9, and that's what it's known for already. And so that, when we took the Cloud Compiler and apply lots of resources, it pushes up this ramp-up curve because we could do way more JIT compiles, way faster, we could deliver it to the application, and as long as latencies between the servers aren't too bad, we get this nice, clean ramp-up curve, a lot faster, and that gets us up to an A. So we've improved startup, we've improved ramp-up. What about throughput? Well, we can do some stuff with that too. Over the years, we've been investing in more compiler optimizations and fixing some bugs too, I have to admit, that caused performance issues. And so over time, as we've been investing in this, it's been pushing the whole curve up. And we continue to do this. This is an area that we continue to evolve and push on and keep pushing things forward and getting throughput all the way up to an A. So we improve startup, we improve ramp up, we improve throughput. What about memory? Let's switch to a different curve because this one's performance. So we got to switch to a memory curve. So this is what our memory curve looked like when we started out some arbitrary time ago, right? We have a whole bunch of memory requirement at the beginning because the JIT compiler is going crazy trying to compile all these methods, and that takes CPU and that takes memory resources away from the application. So not only do these peaks consume memory, but they also take memory that otherwise might be used by the application. So we're actually hurting ramp up by having the JIT compiler active at the same time. So we didn't like these spiky things, so we wanted to have a technology that could get us away from that. And that cloud compiler technology actually was part of that story as well. So sometimes these tools have multiple benefits that we can apply and use them when we deploy them to achieve greatness in many areas. So when we take the cloud compiler, because the JIT compiles have all been taken out, we get this nice smooth, not only just a nice smooth performance curve, but also a nice smooth memory curve. And don't ask me why this line keeps going up. It's not a memory leak, I promise. That's a slide bug, we'll call that. Okay, so our memory footprint is now at a B. That's great, but can we make it even better? And so, yes, we never stop. We're always looking for how to make this better because our competitors never stop, right? It's that effect that Richard mentioned. If you have multiple implementations and they're all being used and they're all being enhanced and helped, then they all have to compete with one another to keep moving forward. And that's good for everybody. It keeps the ecosystem vibrant, and it makes it sure that no matter what JVM you're using, you get great performance because we're all competing against each other. So what did we do? We have a bunch of memory optimizations that we've been doing. I'm not going to go into details here, but we keep pushing this curve down. So even though we were great before, we're still getting better. We're getting even better. In fact, if you run with our checkpoint restore instant on functionality, you'll see even better memory than you would see with our regular JVM, just because we've done a bunch of optimizations and they haven't quite rolled out to all of our deployment scenarios yet. And so in my mind, that gets us all the way to an A. And so in total, we managed to get, over the last 9 years, I think we're pretty close to getting this overall report card. Now, obviously, this is aspirational to some degree. We're always trying to make things better, and we're always investing to make things better. And whenever anybody tells us that they'd like something from it, we take that seriously, and we like that request. So, the more people that we can satisfy with the OpenJ9 JVM and the IBM Summary Runtimes JDK, the better. And we're happy to keep making improvements. And if you have ideas, please. So it's really easy to get. There's a nice, simple ibm.biz get Semru. We'll take you to this website here where you can download. You can see it's available under your usual open source licenses, 100% open source. You can use that instant on technology I mentioned with WebSphere Liberty, and it's really just one thing you have to select as the checkpoint, and you'll be able to start apps running on top of WebSphere Liberty, whether it be Microprofile, Jakarta EE, Spring Boot, or just regular apps, whatever your apps, you can run those on Liberty and use Instant On, and you will get that kind of startup time. The cloud compiler now works with all Java applications. It's available 11 plus in Semru runtimes. One nice thing about OpenJ9 is that it's a single source code base that deploys into all different Java versions. So when we improve OpenJ9 with additional technology capabilities, those memory improvements and those compiler optimizations, they surface in all Java versions. So you're not forced to upgrade your Java version just because you want the latest and greatest performance. You can do it on your timeline when migrating makes sense. And a lot of these have already been delivered to Java 11 plus, and as I said, we keep going. They're freely available, quarterly updates. Everyone can use them for production on a whole bunch of different platforms. And if you need more, please talk to me. And obviously, it's available for free, so you can run it in production. You don't have to pay IBM a cent. We make it completely available for free. All of these technologies, IBM Summary Runtimes is the only place you can get all of these technologies for free without having to pay anyone a dime. But if you do want commercial support, you want that comfort of having the team that built this thing in your corner. If you have a problem in your production scenarios, we have a support offering called IBM Runtimes for Business. It's very cost effective and very cheap and easy for people to get access to. And if you want any more information on that, just feel free to reach out to me and talk. So I'm going to say thank you at this point, and I also have one favor to ask, which is we are trying to collect some info to learn more about how people are using their IDEs. And so please, 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 if you wouldn't mind loading that QR code and filling out a very brief survey to give us some more information about what you're doing with your IDEs. Shouldn't take you very long, and we would really appreciate that information. And I think that's it. Thank you.